So hopefully you were in class today, and if you were, great. If you were not, well, I'm going to just kind of quickly go over some of these things and then finish the notes from today. So we talked about scalar versus vector quantities, and we gave you some examples, and speed versus velocity with the units, and distance versus displacement, and then we have a little graphic where we're starting here, and we're going to walk 3 meters that way, and then we go 4 meters that way. And so from start to end, the total distance traveled is 3 plus 4, which is 7 meters. But the displacement from start to finish is just 5 meters, because it's the hypotenuse of that triangle. Okay? And then we talked about sign conventions for directions. So remember, the wicked witch of the west, she's negative. The good witch of the north, she's positive. So the opposite of those is the opposite sign. Okay, and that kind of goes along with, like, north and up are the same, south and down are the same, west and left are the same, and east and right are the same. Okay, with a few examples of when we use them. Okay, so you have to have directions sometimes, and directions means you have to have a sign. All right, then we talked about constant or average velocity, and so this is when you're moving with cruise control, so the velocity is not changing. And then we talked about when velocity does change, and that would be when something is accelerating. When something is accelerating, that's the rate of change in velocity. And so an object can be doing either speeding up, slowing down, changing direction. It's a vector quantity, which means it has a sign, okay? And it's denoted, acceleration is denoted by an A in a formula. It's an A. And the unit for it is meters per second squared. And I forgot to tell you that in class, so make sure you tack that onto your notes. All right, and then you have your basic equations. So there's 3 equations that have acceleration in them. And this is when acceleration is constant, not when acceleration is changing. But we're not really going to do a bunch of math when acceleration is changing. That seems like ludicrous speed, you know? No, just kidding. All right, so 3 basic equations. So it's kind of like, this is the change in velocity from final to initial, and it's based on the acceleration and the time. So another way to say this is the change in velocity over time. So that might be something on the order of, like, acceleration is v final minus v initial over time. And the way we denote v initial is with a little naught, a little 0 for your subscript. Now, if you have something, if it starts from rest, then that means you're going to have a 0 for your initial velocity. So if we're using A equals v final minus v naught over time, if it's from rest, your v naught is 0, so you get rid of that out of your equation, which means acceleration is v final over time. Okay, you could do the same thing, like if it was slowing to stop. If it was going to stop, then your v final would be 0, and then it would be negative v initial over time. Okay, which makes sense. If you're going in a positive direction and you're slowing down, you'd have a negative acceleration. If you were going in a positive direction and speeding up, you would have a positive acceleration. Okay, and so this is for displacements. This is the change in displacement. This is final displacement, initial displacement. Okay, and so this would be an equation for that based off of the area under the curve for displacement or velocity versus time graph. So your displacement is equal to v initial times time plus 1/2 at squared. I don't really like fractions, so I kind of distribute that and make that at squared over 2, but it's your choice. You do what you want. So I would say if it's starting from rest, you'd have something like that is like delta x is v naught t plus at squared over 2. Your v naught is 0, so v naught times t is 0, so that leaves your equation, which means your change in position or displacement is equal to at squared over 2. So this last one, this is where you have velocity, final velocity squared equals initial velocity squared plus 2a times the change in position, which is displacement. So again, if this starts from rest, then you would end up with, let's see, so v squared equals v naught squared plus to a delta x, right? So if it's starting from rest, then your v naught is 0. So you could say, and if you square root what's left over, you end up with v. So then final velocity is the square root of 2a delta x. Now, if this is a negative operation in here, it's not going to work, right? So it's going to give you no solution. So, but if you are going south, the negatives will cancel out, and you'll end up with a positive number. But if you're going south, then your final velocity is going to have to be negative. So you kind of have to use your brain sometimes, not just your calculator, and figure out, oh, if I'm moving south, then that's a negative velocity. So you have to be careful with things when you have a square root. You have to remember, it is just a number that you're sticking in there, but you have to do something with the sign sometimes if there's a square root. Okay, so here's a little simple example using these equations for acceleration, okay? And if you notice, this one, I have a sprinter begins from rest, okay? And accelerates down a straight track at 1.5 meters per second squared for 5 seconds. What is the sprinter's velocity at the end of this time interval? So I'm looking for final velocity. And how far does the sprinter run? So I'm looking for displacement. Okay, so first one, okay, so if I'm starting from rest, then I know that my v initial is 0 meters per second. It's telling me that it's accelerating at 1.5 meters per second squared, so my acceleration is 1.5 meters per second squared for 5 seconds, so my time is 5 seconds. It doesn't really give me a direction. Like, it just says it's going down a straight track, but it's not, you can't go down a track, like, if you're a sprinter. It's just a track, like it's on the ground. So it's not really telling me a definite direction, so I'm just going to assume everything is positive. And then I'm looking for final velocity. So if I have v initial, a, and time, I can use this equation, the acceleration equation. So for part A, so a equals v final minus v initial over time. But since my v initial is 0, I can just get rid of that. So then I'm looking for just velocity, so I can multiply both sides by time. And so then I get time, which is 5 seconds, times acceleration, which is 1.5 meters per second squared, and 5 times 1.5 is 7.5. And this is velocity, so it's meters per second. You don't necessarily have to write your units until you get to the end. The end unit is important. You do need to make sure you have that. And you need to make sure you're using standard units when you're doing these things, okay? Because if this said 5 minutes, you'd have to turn that into seconds, okay? So for part B, how far does the sprinter run? Well, I can just use the displacement equation, okay? So I can just say, okay, so my delta x equals v naught t plus at squared over 2. So since it's starting from rest, my v naught is 0, so this goes away, and then I just plug and chug. So my acceleration is 1.5 times my time, which is 5, squared over 2. You stick all that in your calculator, and you get 18.75 meters. Okay. All right, so those are some simple things. All right, so let's talk about your graphs, okay? So we're going to talk a little about graphs today, but we'll do a linearization video next class, okay? So for right now, let's talk about our graphs. So if I have a position versus time graph, the slope of that graph is the velocity. And the sign of that graph is the direction. So if I have a stationary object for a position versus time graph that's not moving, so here's my position, which is kind of funny because your y-axis is x for position and your x-axis is t for time. But anyway, I find that funny. X is y. It's weird. Anyway, but if something is not moving, its position is not changing. So your position would be the same as time keeps passing by. So you get just a straight flat line. That's it. If you're going a constant positive velocity, then on a displacement versus time graph, your if it's positive velocity, it's going in a positive direction, which means your displacement is getting higher and higher as time keeps passing. So think of it as it's going this way and this way at the same time. So you end up with a straight line with a positive slope. And it has to be a positive slope because the sign is telling you the direction. It's positive velocity, positive slope, positive direction. So if we're going a constant negative velocity, okay, so that means my direction is in the negative direction. So think of my direction as going down the y-axis as time goes that way, which means I would end up with a straight line with a negative slope. Okay, so that would be my position time graphs. Velocity versus time graphs, the slope of those is the change in rate of velocity. So the slope is the acceleration. Okay, and if you have a flat line, if a equals 0, you have a flat line. Okay. So for these, for a stationary object, it's not even moving, so it has no velocity at all. So it has no velocity and it has no acceleration. So I like to draw my velocity time graphs as having a positive and a negative quadrant. So my v is my y-axis and my t is my x-axis. So I'm going to draw that for all of these. So if it's stationary, it's not moving, its velocity is 0, so you'd have a line on the 0. If it's got a constant positive velocity, it's not changing velocity, so you'd end up with a straight flat line, but it would be in the positive quadrant. If you have a constant negative velocity, it's going in a negative direction, but it's not changing its velocity or direction, so you'd have a straight flat line in the negative quadrant. Okay, so negative constant velocity there. Now, for all of these, if you had an acceleration versus time graph, they are all at 0, so you would have a line for 0. So for everything in here, your acceleration versus time, your acceleration is 0. So it would look like that. Whether it's moving or not, if it's not accelerating, then it just has a flat straight line at the 0. Okay? Now, if something is changing its direction, it's accelerating. Or if it's speeding up or slowing down, it's accelerating. So if something is speeding up in a positive direction, then you have positive velocity and positive acceleration. If you are speeding up in a negative direction, you'd have negative velocity and negative acceleration. So if something is speeding up, okay, so for speed up, V and A signs are the same. Okay? The direction for both, for these, so for both of these, if it's speeding up, the V and the A signs are the same. Okay? The direction is dictated by the velocity. So that's for all of this page. The direction is determined from sine of velocity. So if something is slowing down but in a positive direction, it's going a positive velocity because it's a positive direction, but if it's slowing down, then it has a negative acceleration. It's decelerating. Okay? If something is slowing down in a negative direction, so if it's going in a negative direction, it's going to have a negative velocity. So if it's slowing down, its sign of acceleration is going to be opposite, so it's going to be positive acceleration. So for both of these, you have that for an explanation. For both of these, if you are slowing down, so if you slow down, your V and A signs are opposite. Okay, so those are the signs. Now, position versus time graphs. Okay, so for my position versus time graphs, they're just all going to be x versus t. Okay. Now, if I'm speeding up and I'm going in a positive direction, then my slope needs to be positive, because the slope of the position time graph is the velocity. So if the velocity is positive because I'm going in a positive direction, then it's going to have to be positive. If I'm speeding up, that means I'm going kind of from 0, which would be a flat line, to a steeper and steeper, but it has to be in the positive direction. So I'm going to go from 0 to that. So that's the graph of position versus time for speeding up in a positive direction. Now, if I'm speeding up in a negative direction, it's going to have a negative slope, okay? So because my direction is negative, my velocity is negative, but I'm speeding up, which means I'm going to, again, start at 0, but now I'm going to go down and make it more and more steep, but in the negative, okay? So then I'm going to go, it's like a slide that you fall off of, okay? So that's speeding up in a negative direction. Now, if something is slowing down, it's going to start at a high speed and then go to 0, okay? So then you just have to determine, well, which way is it going to go with that? So if you're slowing down in a positive direction, that means my slope has to be positive. So it's going to go from steep to flat, but with a positive slope. So it's going to go from steep to flat, but with a positive slope. Now, if I'm slowing down in a negative direction, it has to go from steep to flat, but with a negative slope. So we're going to go steep to flat. Okay? So those are all your position versus time graphs for each of these things. Velocity versus time, so I would make all of them kind of like a sideways T. And same thing with my acceleration graphs, I would make all of those a sideways T. So, for the speeding up in a positive direction, the slope of this line is changing. It is always positive, but it's changing. It's getting higher and higher. So it's going from 0 and getting to a higher and higher positive number. So for this one, it's going to be 0 to a higher and higher positive number. So the slope of this line is positive, and since this is a straight line, it's just one number all the way. So it's a positive number. So your acceleration versus time will be positive in the upper positive quadrant, and it will be a straight flat line. So this is for constant acceleration. For speeding up in a negative direction, I'm going from 0 and then steeper, but this has a negative slope, so these are going to be negative numbers. So I'm going to go from 0 to a higher negative number. So that's going to be a straight line, but with a negative slope, okay? So since it has a negative slope, my acceleration versus time, it's going to be a negative number, but it's not going to change. So it's going to be a flat line, but in the negative quadrant. For my slowing down in a positive direction, I'm going from a high number to 0, but in the positive quadrant. Okay, so high number to 0, but in the positive quadrant. And it has a positive slope. Yeah, a high positive to 0. So a high positive to 0 is going to be in this quadrant, like that. Okay, so it's a high number and it approaches 0. Okay, the acceleration here So the slope of this line is negative, which means I have negative acceleration, but it's straight, so I'm going to have a line in the negative quadrant right there. Okay? Now, this last one, I'm going from a high negative number to 0. So I'm going to be in the bottom, the negative quadrant. I'm going to go from the bottom to 0. Okay? Now that's a straight line with a positive slope. So this one is going to have a straight line in the positive quadrant, straight flat line. Okay? And those are all your graphs. So the next video will be more about graphs and an example and linearization. Bye-bye.